All right, in this video, we are talking about key attributes of log functions. And for key attributes, we're referring to the intercepts and max and min on intervals. So when we start finding max and min on intervals, it's going to be helpful to have a sketch of the graph. It's also helpful to have a sketch for intercepts, but for max and min on intervals, we really want to know if it's an increasing or decreasing function. And so whenever you're working with log function, with a base that's bigger than one, like 2, 3, or 4, the default setting is increasing. That's the parent function. Okay, it kind of looks like square root going up to the right and then down towards the asymptote. And so whenever you're deciding increasing or decreasing, act like you have a person traveling from left to right along this curve. If they are climbing, that it is an increasing function. Okay, and so if we have a reflection across the x-axis, the function will now be going down, and then I call this the tail, the one that's approaching the asymptote. It's tail up. And so now this is a decreasing function. So a reflection across the x-axis results in a decreasing function. He's going down the mountain. Okay, same with the reflection across the y-axis. It's still tail down, but now it's facing to the left. And so as this person travels along the curve, he is descending down the mountain. So this would also be a decreasing function. So anytime you have one reflection, whether it's across the x-axis or across the y-axis, it's going to result in a decreasing function. If you have both reflections, and so it's tail up because of the reflection across the x, but it's also facing left, we're actually back to increasing. If we travel from left to right, this is an increasing function. Okay, so one reflection, it's decreasing. Two reflections, it's increasing. The other thing I want to point out about this graph is that because of the vertical asymptote, we may or may not have an y-intercept. Okay, so here none of these functions have a y-intercept because the y-axis is the asymptote that we are approaching but never touch. And so if I have transformations that move this graph to where it does cross, we could have a y-intercept. And so it's always kind of helpful to picture whether or not you are going to have a y-intercept or not. And that's also true for max and min. Depending on where the asymptote is, that's going to affect whether or not we have a max and min on a given interval, because it approaches negative infinity or it approaches positive infinity as it approaches the asymptote. And so that could affect our max and min. Okay, so to find an x-intercept, that is the point where y is 0. And so when we're writing the ordered pair, you're looking for an x value when y is 0. Other names include roots, zeros, solutions, all referring to x-intercepts. We have 4 names for that. Okay, and so algebraically, we would plug in 0 for the y value and have to solve for x. Okay, and so plugging in 0 for the y means plugging it on the left side. And so that leaves me with the equation 0 equals -2 log base 5 of x minus 3 plus 4. And so as we're solving for this x, the first thing we have to do is isolate the logarithmic expression. So here's the log with its argument. And so my first step is to subtract 4 from both sides. That leaves me with a -4 equals -2 log base 5 of x minus 3. Okay, again, we're still trying to isolate the log. And so my next step is to divide both sides by this -2 that we're multiplying by. And so that leaves me with the equation 2 equals log base 5 of x minus 3. Okay, and so once you've isolated the logarithmic expression, you're ready to convert it to exponential. That's the only way to get x out of the log, is to convert to exponential. And so we're working with base 5 raised to the second power equals x minus 3. base 5 raised to the second power equals x minus 3. And so 5 squared, of course, is 25. And then we would just add 3 to both sides to get an x value of 28. And so don't leave that as an equation. That looks like an asymptote. And so you want to write it as an ordered pair to avoid any kind of confusion. 28, 0 for our x-intercept. Okay. For the y-intercept, this is the point where the x is 0. And so when we write it as an ordered pair, the 0 goes in the x spot, and we're looking for a y value. And so as mentioned above, depending on the location of the vertical asymptote and the log, we may or may not have one. And so looking at this example, picturing the graph, I know that the vertical asymptote has been moved right 3. And I have a reflection across the x-axis. It's vertically stretched by 2, and it's moved up 4. And so if I sketch this graph, the vertical asymptote is at 3, and the x-intercept, which is usually 1 away, has been moved up 4. And it is tail up because of the reflection across the x-axis. And so because we're still to the right of our vertical asymptote, notice we never cross our x or our y-axis. And so graphically speaking, we know there is no y-intercept. It never crosses the y-axis. Algebraically speaking, we would plug in 0 for the y, and I call it number crunching, and so really we're simplifying or evaluating. And so plugging in 0 for, not 0 for y, 0 for x. We're solving for the y-intercept, so plug in 0 for the x. And so when I plug in 0 for the x, I get -2 log base 5 of 0 minus 3 plus 4. Okay, and so that gives me -2 log base 5 of -3 plus 4. And you can't plug in a negative argument to a log. If you type that into your calculator, you're going to get a non-real answer. And so just to show you, log base 5 of -3. Non-real answer. And so when you see that, a red flag should go off. You can't have that. So no solution here. And so you would say no y-intercept. Okay, next we're going to talk about max and min on intervals. So this is where we care about whether the function is increasing or decreasing, because when we are talking about an increasing function, as long as the vertical asymptote isn't on the interval, it will occur at the right endpoint. Okay, if we're trying to find the minimum, an increasing function, the minimum will occur at the left endpoint. But again, we really have to sketch this in order to see what's happening. And then for decreasing functions, it'll be the opposite. Okay, so looking at this example, we're still working with the same function. And so I'm going to grab the graph here so that we have something to look at. Okay, so it's been reflected across the x-axis, so it's tail up, and then we have a vertical asymptote at 3. And so it is a decreasing function, and now we just need to graph our interval. And so remember, when you're given an interval, those are x values. X equals -4 to x equals 5. This is our restricted domain. And so if I graph that interval, negative 4 is over here, and positive 5 is over here. Okay, and so trying to find a maximum, my vertical asymptote falls right in the middle of this interval, so this function is going to keep going all the way to infinity as we approach the asymptote at x equals 3. And so on this interval, there is no maximum on the interval. Anytime the vertical asymptote falls in the interval, you may or may not have a max, or you may or may not have a min. We do actually have a minimum, so that's going to be this next question. And so here's my graph. We're still working with the same interval. And so from -4 to 5, this function is approaching positive infinity, so there's no maximum, but then we do reach a minimum on this interval. It occurs at the x equals 5, okay? And so the minimum occurs at the endpoint x equals 5 because it's a decreasing function. And so now I know I need to plug in x equals 5 to my function. So -2 log base 5 of x minus 3 plus 4, and we are plugging in the 5. And so that would give me -2 log base 5 of 2 plus 4. Now, because this 2 is not a power of 5, there's no way we can simplify that log to a nice number. And so this is when you would use your calculator to get a decimal approximation. Okay, and so -2 math alpha math base 5 of 2 outside the parenthesis plus 4. And so this value is approximately 3 point, and usually they have 1 decimal point, so we'll do 3.1. And so the minimum value would be 3.1. So on a multiple choice test, if this was asking for maximum, you would say none. If it's asking for minimum, you would say 3.1. It's always just a y value. All right, so we're going to do 3 more examples of looking at different functions. And so for each one, we're going to find the x and y intercept and max and min on a given interval. Okay, and so looking at this function, let's do it algebraically. For our x-intercept, we are plugging in y equals 0. And so we plug in 0 to the left side of the equation. Then we have 2 log base 2 of 3 minus x plus 4. Again, we are trying to isolate the log. So I like to put a box around it so you can see the log and its argument. So my first step is to subtract 4, which gives me -4 equals 2 log base 2 of 3 minus x. And then we still have a 2 that's being multiplied, and so now we divide both sides by 2. So that gives me -2 equals log base 2 of 3 minus x. Now we're ready to convert. 2 to the -2 power equals 3 minus x. 2 to the -2 power equals 3 minus x. 2 to the -2 is 1 over 2 to the positive 2. And then 2 squared is 4. And then to isolate x, subtract 3 from both sides, which would give me a -2.75 equals -x. Divide both sides by a -1. We get x is positive 2.75. It does say round to the nearest tenth, even though this is a nice decimal, and so I'm going to follow those directions. And so we would say 2.8, 0. I don't like that, but following directions. Okay, for the y-intercept, we're plugging in x equals 0. So that gives me y equals 2 log base 2 of 3 minus 0 plus 4. Just grabbing the original equation. Of course, 3 minus 0 is 3. And because 3 is not a power of 2, we have to use our calculator to simplify this. Oop. And so 2 math alpha math base 2 of 3 plus 4 gives me approximately 7.2. Okay, and so as an ordered pair, 0, 7.2. Right, now we're ready to find max and min on our closed interval, and we're going to need the sketch. And so I'm going to write the equation, but we need to rewrite it so it's in proper transformation form. So in proper transformation form, we would need the x value first, followed by that positive 3. And then if there's ever a value in front of the x, you need to factor it out, and you do that by adding parentheses and dividing by whatever that value is. In this case, it's a -1. So this would read 2 log base 2, sorry, I always forget to write the base, 2 log base 2 of negative x, and then 3 divided by -1 is -3. Okay, and so now I can see this function has been moved right 3. And so we have x equals 3 as our vertical asymptote. It's also been moved up 4 and then vertically stretched by 2. And something that's super important is the reflection across the y-axis. Okay, and so when I make my sketch, graph the asymptote first. 1, 2, 3. And then it is reflected across the y-axis. And so instead of having my x-intercept to the right, my x-intercept is now to the left. It's reflected across the asymptote. And then it is also moved up 4 units. And so it is up here for that critical point. Okay, and so it is still tail down towards the asymptote and then up to the left. And so I can tell this is a decreasing function. Imagine a person climbing on this. This is decreasing. And so now we're ready to graph the interval, which is x equals -3 to x equals 7. So x equals -3 to x equals 7. And so once again, the vertical asymptote falls on the graph in the middle of the interval, but this time it's going down towards -infinity. So I know this function doesn't have a minimum, and then our maximum would occur at the left endpoint. So this is our maximum, and then no minimum. Okay, and so this particular question asks for the maximum, and so the maximum occurs at the x equals -3. So we would take our equation. I'm going to take the original equation, 2 log 3 minus x, and then there's a plus 4 at the end. Okay, and we are plugging in x equals -3. And so when you see that 3 minus negative, that turns into a 3 plus 3. This is still base 2 of 6 plus 4. And then 6 is not a power of 2, and so we do need our calculator to simplify this. So 2 math alpha math base 2 of 6 plus 4. And so our y value is approximately 9.2. And so that's what we would say for our maximum. And then instead, if we were trying to find the minimum, we can see from our picture that there is no minimum. In the middle of these green lines, we have that vertical asymptote where the graph is continuously going down to negative infinity, so it will not reach a minimum. All right, in this next example, to find the x-intercept, we plug in 0 for the y, so that gives me 0 equals negative log base 4 of 2x plus 9 minus 1. We need to isolate the log. So first step is to add 1. And then we have a negative, which is technically a negative 1. So we need to divide by negative 1. So that gives me negative 1 equals log base 4 of 2x plus 9. We're ready to convert. Base 4 to the negative first power equals 2x plus 9. Base 4 to the negative 1 power equals 2x plus 9. 4 to the negative 1 is 1 over 4. And then if you want to get rid of that fraction right off the bat, you could scale the entire equation by 4, which would give me 1 equals 8x plus 36. And then we can subtract 36 from both sides, which is negative 35. And then divide by 8. And so x equals negative 35 over 8. And then we can use our calculator to get the decimal approximation. Negative 35 divided by 8 is going to be negative 4.4 as we round to the nearest tenth. Negative 4.4. And so negative 4.4 comma 0. For the y-intercept, we plug in x equals 0 and simplify. So I have negative log base 4 of 2 times x plus 9 minus 1, and we're plugging in 0. And so that gives me negative log base 4 of 9 minus 1. 2 times 0 is just 0. And because 9 is not a power of 4, we need our calculator. Negative math alpha math base 4 of 9 minus 1. Okay, so that's about 2.6, negative 2.6. And so 0 comma negative 2.6. Okay, for max and min, we need a good graph. So first step is to put it in proper transformation form, meaning we need to divide by this 2 or factor out the 2. And so that is going to give me 2 and then x plus 4.5 minus 1. Okay, that means my vertical asymptote is x equals negative 4.5. We've also moved down 1. We've horizontally compressed by 1/2, but we don't really have to consider that for our picture. we do need to consider the reflection across the x-axis. And so starting with the asymptote, we have negative 4.5. So right in between negative 4 and negative 5. Okay, and then it is reflected across the x-axis. And so the tail is going to be opening up, and then we're going to be going down to the right. And we've moved down 1, so my x-intercept is now at the negative 1. So now tail up, down to the right. So it is a decreasing function because of the reflection. And now for our interval, we have negative 5 to negative 2. So negative 5 to negative 2. Once again, our asymptote falls on the interval. And so we are approaching positive infinity. So there is no maximum on this interval. Okay, for the minimum, we can see that the minimum occurs at the x equals negative 2. So minimum at x equals negative 2. It is going down, and it does not get lower on the interval than at the negative 2. And so I'm going to grab the original equation, y equals negative log base 4 of 2 times x plus 9 minus 1, and we're plugging in negative 2, which gives me negative log base 4 of negative 4 plus 9 minus 1, negative log base 4 of 5 minus 1. And then because 5 is not a power of 4, we are going to use our calculator. Negative math alpha math base 4 of 5 minus 1. So approximately negative 2.2. And looking at our graph, we can see it is negative, and so that makes sense. So your minimum value, negative 2.2, but there is no maximum. All right, in this last example, we are working with natural log. And so x-intercept, same thing. We set y equal to 0, and so my equation would be 0 equals natural log of x plus 4 minus 5. First step is to isolate the log, and so in this case we have one step and we just have to add the 5. So that gives us 5 equals natural log of x plus 4. And then we are ready to convert. So remember, for natural log, our base is e. And so e to the 5th power equals x plus 4. So last step, we just need to subtract 4 from both sides. And so x equals e to the 5th minus 4. They want the decimal approximation. And so in our calculator, we would type second ln, and then our exponent is 5. Get out of the exponent, minus 4. And so our x-intercept is approximately 144.4. Okay, for the y-intercept, we plug in x equals 0. And so my y value would be natural log of 0 plus 4 minus 5. And so that simplifies to natural log of 4 minus 5. And so the decimal approximation, and these would likely be on the non-calculator test. And so you would just leave it in terms of log, but here they want the decimal. And so y is approximately negative 3.6. Okay, for this max and min, picturing this log, e is approximately 2.7. And so our base is approximately 2.7. There's no reflection. And so we have just moved left 4. So the vertical asymptote is at x equals negative 4. And the x-intercept has moved down 5. And so down at negative 5. Okay, but it's still opening up to the right and then down towards the asymptote. And then for our interval from negative 1 to 3, we have negative 1 to 3. You can see that the asymptote is not on this interval and it is increasing. And so my minimum is at the left endpoint and my maximum occurs at the right endpoint. And so for the maximum, it is at the x equals 3. And so grabbing the original function, we have natural log of 3 plus 4 minus 5, which is natural log of 7 minus 5. And if you type that in your calculator, you get approximately negative 3.1. And so negative 3.1 would be your maximum. Okay, and then our minimum is going to occur at the negative 1. And so the y value would be natural log of negative 1 plus 4 minus 1. And so that is natural log of 3 minus 1. And if you type that in your calculator, you get negative 3.9 after you round it. Okay, and so notice my maximum, negative 3.1, is bigger than negative 3.9. It's less negative, so it is bigger.